Thanks.
They're also argue very strongly, and that's they spoke about both of them. So and trying at this and so I kind of
talking about their result of that.
yeah, very strongly. There's original the other 15 are all 2015 first defense is shared. 30, 40, Kelvin.
3 of those have an identity.
And so
the probability.
So you get not one fit of all the operators are one state short. It's causing a general
So in this diagram,
it's hard to
this is not just going over to the right side.
So they're saying it's right in this video.
It ends up with the input is like the last operator and whatever you've got to. Basically, what I
Where in the gate, I labeled the gate as my right side of the gate. So in one layer, it creates 0, 2, 4, 6. And the next layer, the gates are on 1. So because of my label,
Für dich ist nicht viel Neues dabei, glaube ich.
Hätte ich mich nicht vorne hinsetzen.
Jetzt in den Colorado Creek gehen und die abkühlen.
Ja, das wäre nicht schlecht.
Mhm.
Wobei es eher so aussieht, als würde es gleich gewittern.
Stimmt, das ist eher dann gefährlich.
Ja.
you know, if it violated some thermodynamic identities, that then I could understand. If it shows interesting curves, that's reminiscent of which are nevertheless different. That's interesting.
I see. Okay, so in that sense, this is really. Yeah, you know, because I've been hearing the other side.
Yeah,
like the past.
Okay.
I just had yeah. I'll. Okay, great. Okay.
The first one is numerics. Yeah.
Okay. All right, let's go ahead and get started. So it's a pleasure to have Frank Pollmann here from Munich. He's going to be talking to us about numerical methods in quantum many-body dynamics for the first 2 lectures.
Okay, thanks, Sarah, for the introduction and for the organizers for putting together this really nice school and giving me the opportunity to teach at the school, which is fun. So just a few words before I start. So I created a collection of links to some notes and also to some tutorials that will be useful to demonstrate some of the ideas that I'm going to discuss in the lecture today. And in the first 2 lectures, I mean, maybe this one and the one tomorrow, I will discuss about numerical methods that can be used for studying lattice model dynamics. And on the lecture on Thursday, I will shift gears and talk about Hilbert space fragmentation and constraint dynamics. So the overview of the lectures today and tomorrow is given here. So I'm first going to start by giving a little bit the idea about why these methods that I'm going to introduce are going to work. For this, I want to discuss a bit of entanglement, and in particular the area law. And then I want to tell about the kind of backbone of everything that I'm going to discuss, and these are matrix product states. So matrix product states are an efficient way to compress quantum many-body states, as I will argue. And based on these matrix product states, there are many algorithms that use this, and I picked 3 algorithms. So the first one is particularly simple and quite useful because it allows us to do a time evolution of quantum many-body states, and also finding ground states using imaginary time evolution. And then I'm going to discuss a variational method to find ground states within the manifold of matrix product states. And lastly, I'm going to discuss some ideas about doing the evolution in an operator space. So here we will extend basically the concept of matrix product states to describe operators, and that allows in certain cases for more efficient simulations. So the program is quite full. So let me jump right into it, and I first want to motivate the whole idea and also tell what kind of problems you will be able to address with the techniques that I'm going to discuss. So in particular, I want to consider for this class only one-dimensional systems. So we assume that we have one-dimensional lattice, and these can be spins, that can be bosons hopping on some lattice, you name it. But the important thing is that we have now some lattice, and we are saying that we have a system made out of L units, or like of L sites. And the many-body Hilbert space that we have to consider in this case would be C to the power of D L, and D here is now the local dimension now and throughout this lecture. So basically we have here local Hilbert spaces described by some states I n, where I n is going from 1 up to D. So now I can write down a basis for my many-body Hilbert space, which is the tensor product of my local states IL, and the right. So here we have now the tensor product of our local Hilbert spaces. And in the case of a spin 1/2 system, and this is what I'm mostly going to discuss in this course, and but also was discussed like in the previous lectures, D is simply 2 for a qubit 0 or 1, or for a spin up or a spin down. So now we've got everything set up, and now maybe connecting to the lectures that were taught before, we might say that, well, we have now a given Hamiltonian, or we have a Floquet circuit, and now we want to see whether after a sufficiently long time the system actually thermalizes. Or we might want to consider certain quench protocols. We want to see how entanglement is spreading through the system. Or we might have a Hamiltonian. We want to figure out what is actually the ground state of this Hamiltonian. So these are the types of questions I want to address. And for doing this numerically, the most general form, what we can do is we can now write down the many-body state as just being a superposition where we have summing over all degrees of freedom that we have, like for each spins up and down. And then we have now the amplitudes of a many-body wave function, psi I1 through IL, times our product state of the basis I2 to IL. Good. So now we can already sit down and do this exactly on a classical computer by by just literally constructing the full basis of the Hilbert space. In this basis, we can now represent our Hamiltonian as a big matrix and diagonalize it. And then we can look at the ground state, so lowest energy eigenvalue of this big matrix, or we can do some time evolution of some initial state. So having done this work, we can now calculate whatever we want. But the caveat is that the Hilbert space is growing exponentially, and that really limits us to fairly small system sizes if we want to do it numerically exactly by working in the full Hilbert space. And the big question, and this is what I want to address, like how to compress quantum states, or quantum many-body states. And the answer to this will be the matrix product states that I already mentioned. And what this will buy us, in particular, looking at dynamics, right? So if we, for example, want to start from some simple initial state and evolve it with respect to some Hamiltonian, what it buys us is that we can now go to much larger systems when using these matrix product states. And a nice plot to illustrate what we will be able to do, what we couldn't do before, is the following. We could say that, well, let us now have a diagram where we have here the time over which we want to evolve the system. And here we have the system size. And we just might consider just simply a spin 1/2 system to just add some numbers to our graph. Then we could say that, well, if we are using exact diagonalization where we're representing our Hamiltonian exactly, well, we can just evolve a system as long as we like to, but we are limited to fairly small system sizes, and the largest that we can reach is of the order of, say, the order of 30 or so sites. And then even maxing out all the tricks that we know of, this is basically where it's going to stop. Now, the new idea when using these matrix product states, well, we won't be limited in system size, and in fact, we can work directly in the thermodynamic limit, at least for translation invariant systems, but we will be limited in terms of the time over which we can analyze the system. And in certain cases, it actually helps that we can go to much larger system sizes, albeit we were going to be limited to shorter times. Good. So having said this, I will now tell you how we can do this compression and for which kind of states we actually will be able to do this compression. And this also is going to connect to the fact that we are limited in terms of the time that we can evolve a system for. So now, sure.
So presumably you can evolve further. You just don't trust the wave function because it becomes more entangled than the matrix product state. Is that the statement?
Well, the statement is the following. What I can basically think, if I'm going to touch up on this later on, but let me briefly just make this point. So let's say that this is a volume of our Hilbert space, and now, as we're going to see in this matrix product states, we have a parameter which is the size of how big the matrices can be, and if we just draw it, then we're going to have a manifold of states which are actually captured by this. And if we now start from a simple product state which we want to evolve, it's clearly going to be in this manifold. But then at some point, if you just do that following the trajectory of a state, we're going to leave this. And once you're going to leave this, you have to adjust the size of the dimension. At some point, that becomes a bottleneck. At some point, in principle, you could span the full Hilbert space, but then you are just running again into memory issues.
It's because the wave function is getting more and more entangled.
That's correct, yeah. Mm-hmm. But this is exactly what I'm going to discuss now. So now exactly why this is a good segue. So now let me discuss a bit about entanglement and the area law. So we already heard quite a bit about entanglement was mentioned in several lectures before, but there are, of course, many ways how our degrees of freedom can be entangled, or different kind of measures that we can use for measuring the amount of entanglement. And what I want to consider is the bipartite entanglement of our system cut into two segments. So in particular, this is now our one-dimensional chain. And now I want to do a bipartition. So I want to cut my systems into two parts. I'm having now my subsystem A and subsystem B. And now I want to look at how the degrees of freedom in A are entangled with the degrees of freedom in B. And this is measured by various quantities. I mean, we could, for example, measure the entanglement entropy or the von Neumann entropy for the reduced density matrix. So we have then, well, let me just write the trace. So we have a minus the trace of rho A of log rho A. And this is the von Neumann entropy, which I'm going to talk about. So this is now a measure telling us how, when cutting my chain into two halves, are entangled. And now in this context, and this is going to be a very important tool that we're going to use over and over again, I want to introduce the Schmidt decomposition. So now we keep the same bipartition that I advertised here. So we're just cutting our system into two halves, and I can do this roughly in the middle, but I can do this like at every bond that I'm thinking about. I'm just picking one bond in which I'm doing this decomposition now. And now what I'm doing for the Schmidt decomposition, let me just write it in orange because I'm going to refer to it many times. So now we could say that we have our many-body wave function as defined up there, and I'm going to write it as a sum over alpha from 1 going up to the minimum of the dimension of A or the B. Right? So whatever Hilbert space of those is smaller. And now we have here lambda alpha, which are the Schmidt values. And then we have here states, which I call phi alpha A, phi alpha B, right? So every quantum many-body state can be decomposed in this way, and I can now sort these values. So I just sort them according to their size. So the lambdas are always real and positive, and I can sort them in this way, which is going to be important later on. And they're just going to be larger than 0. And the Schmidt states are orthogonal. Right? So the Schmidt states phi alpha prime are orthogonal. So now, if you have this decomposition of the state, it's actually fairly easy to show. And if you don't see it right away, I encourage you just to quickly plug it in. But if you take this wave function, knowing that the Schmidt states are orthogonal, then you see that the reduced density matrix, which we have here, right? So the reduced density matrix is the where we trace out subsystem B from the full density matrix of our state psi. Then we find that the reduced density matrix A is simply given by the sum over alpha, where we have now lambda alpha squared times the projector onto the eigenstates. Right? So if we have Schmidt decomposition, we can just directly construct we basically can directly calculate the entanglement entropy from the eigenvalues of the reduced density matrix. Good. So since the Schmidt decomposition is very important for understanding how we can compress quantum states, I want to just provide some intuition about this Schmidt decomposition and how the Schmidt coefficients look like for a few simple cases. So the first is a simple product state. So if you have a product state, I don't know, if you just have a product state, maybe just a state. In this case, we find that lambda 1 is equals to 1, and all lambda for n larger than 1 are 0, right? And then these are immediately the dominant Schmidt states that we have. If we take, and accordingly, the entanglement entropy is 0. This is a non-entangled state. Then, as another example, we could take a dimerized state, for example, dimerized state of the form where we would say that we, for example, form Bell pairs of neighboring spins, and if we just do a bipartition across one of those dimers here, or one of these Bell states, so let's say that these guys here just correspond to the sum from I from 1 up to D over I on 1 and I on spin 2. Now, for this particular case, we find that lambda for some alpha smaller equal D is equal to 1 divided by square root of D, and all lambda alpha which are larger than D are 0, and the entanglement entropy S would simply be log D. Now, one last example, and this would be a random state. So basically, the experiment that I want to do now is I just take my many-body Hilbert space and I just picking a random state. So numerically, what I would do is I just choosing random phases. I just write down the vector for describing a many-body state, and I'm just picking the amplitudes and the phases randomly, and then I find a state which is actually maximally entangled. Random state. So if I draw the random state, I would just draw lots of entanglement between the degrees of freedom. And in that case, what I'm going to find is that the entanglement entropy is actually L half times, if I just cut it in the middle, L half times ln of D minus 1/2. And this has been shown by Page sometime in the 90s. So we see that, and this is an important takeaway message, that we have certain states, like the product state and the dimerized state, where we just really have only a finite number of non-zero Schmidt values. But if we take a random state, we actually see that the entanglement entropy follows like is proportional to the system size, and as a result, we see that the Schmidt values are roughly flat. So we would find that the Schmidt values lambda alpha will be approximately each 1 divided by the square root of 2 to the, or like D to the L half. So here we would find that all Schmidt values roughly contribute equally to the Schmidt decomposition. And that will be actually an important part, because, and I'm already alluding to this briefly now, because if you're having states of this type and you're just doing the Schmidt decomposition, you see that instead of having here a sum over exponentially many states, we can actually just stop after a few, and we can just, in these cases, exactly represent the state by taking only into account a few Schmidt values, and here we would have to take into account all of them.
Little d to the capital L.
This one here, right? So if we take now a decomposition of this type, so if we so then this here would be dA would be d to the power of I don't know, maybe L minus small l, and this would be then the other part. Yes.
For the random state attribute, is there an expectation value of the state? Or like maybe I don't understand what you're doing. So that's actually quite neat. So if you have a large system, so if you just assume that the system, if L is very large, then you're actually going to find this value for the entropy with zero, like with a variance which is going to zero.
Sorry, what one is 0?
The variance of that set of riches, yes. Good. Yeah, we're going to come back to this again later. Good. Now let me just quickly state the area law. So the area law is now doing the following. So in general dimensions, we now take a some hypercube of dimension L times L, and we just cut it into 2 halves. And what we're going to find, and this is now the area law, that ground states of local Hamiltonians, local and gapped Hamiltonian fulfill the area law. And the area law states that the entanglement entropy between the 2 parts is proportional to L to the power of D, where D is now the spatial dimension, minus 1. And in fact, in dimensions D larger than 1, this is a conjecture, but there is a proof by Hastings for 1 dimension. So for D equals to 1, there's a proof by Hastings. And that proof is based on the Liebschultz-Mattes theorem applied to imaginary time evolution. But I'm not going to discuss this in detail, because the reason why I'm going through this exercise is just I want to motivate why we are able, or motivate the strategy that we use for compressing quantum states. But for the special case of 1 dimensions, it means that S of L, like this is now exactly the entanglement that I do before that, as I'm cutting my 1-dimensional system into 2 equal halves, that this is equal to a constant, assuming that L is now larger than the correlation length I have in my system. Right? So I'm being a bit fast here, I guess, but the point is that there's also, whenever we have a local and gapped Hamiltonian, we also know that the ground state will have a finite correlation length. So we have this kind of length scale given, and there's all we do is that we're assuming that our system size is large compared to this correlation length. And the intuitive picture for this is that if we have a ground state of some local Hamiltonian, now we have with a correlation length psi, then we will have quantum fluctuations only over a length scale of psi. And if we make our system larger, then we will see that, well, the new sites that we just add to the site will not contribute to the entanglement between the 2 parts A and B, but instead they will just be kind of live only in A or only in B, and thus we get find that the entanglement entropy between the left part and the right part is independent of the system size L. Yes? No. So that's a good point. So because like this on the very beginning, I said that, well, if we say that, well, what is the entanglement of a state? We have to be actually more precise in that. We have to say that the entanglement with respect to which kind of partition are we talking about? And that's why I was careful to just define my partition as a contiguous partition where I say that's cut it into 2 halves. If instead you were to do a partition where you say that, well, we have maybe A sites and B sites, then we would find a volume law. And you can also just argue why this would be the case, because you would find that basically within the correlation lengths, you just add more and more entanglement as you make the system larger. Yes?
Like for a single dimer, I see it's 1/√D.
Yes.
But what are the, and I know the other dimers don't affect the entanglement entropy, but in terms of Schmidt eigenvalue, they don't affect this. What are the other?
Right, I think this is a good point. This is also exactly helping with the future. So let us now explicitly write down the corresponding Schmidt values, maybe for a spin 1/2 system, right? So let's say that D is equals to 2, and now, right, so now we have our system where we, like, this is a full system, and now we just do a Schmidt decomposition here. And the corresponding Schmidt values would be the following. So alpha equals to 1 would be the one where we have a dimer here, and then we have maybe occupied, and alpha equals to 2 would be, we also have the dimer here, and this side empty. Come again? The cut is now here on the dimer, and the corresponding other states, right? So if I say that my dimer state is the one where we have, like, that we're just superimposing these, then then this would be the Schmidt states for my A side, for the A half, and for the B half correspondingly, these would be then the states where this one is also occupied, and this one is in a dimer state, and here.
Oh, I see. So
the Schmidt state contains
Schmidt eigenvalue is not affected by all the other dimers.
That's right. So the Schmidt state far away, and this is actually quite interesting. So if you now take a ground state of a local Hamiltonian, and you would look at the Schmidt states, just I don't know how to graphically how I would like to write. So if I just now have my state, and this is, and I did a cut, maybe here was a cut done, then I would find that, well, the Schmidt state has here some fluctuations, but far away from the cut, the Schmidt state will actually be identical to the ground state. So the Schmidt states will only be different from the ground state in a region which is given by the correlation length of the system.
But the Schmidt state is independent of how you, oh no, it does depend on that.
It does depend on the cut, yeah. Mm-hmm. Good. So, yes?
Other example to area law in pair dimensions.
Well, I mean, I know ground states of gapless Hamiltonians which violate the area law, and that would be, for example, every state that has a Fermi surface. If you have a Fermi surface, you don't find the area law, but you have some leading log corrections. But I can't tell of any counterexample of a gapped Hamiltonian that violates the area law. Yes?
Is there an easy way to understand the log contributions?
Right. So in 1D, yes. So in 1D, let me say so this is for gapped Hamiltonian, and if you have 1D gapless, then we're going to find that the entanglement entropy is proportional to the logarithm of L. And in this case, if you take, for example, ground states that are described by a conformal field theory, you can just explicitly calculate it and see that you get the logarithm. And in this more intuitive picture, you would say that, well, if you don't have a correlation length, right? So here I made the argument saying that, well, you only have quantum fluctuations over a certain length scale. But if you have a correlation length that diverges, which is the case if you have a gapless system like described by a CFD, for example, then you would see that, well, every spin is entangled with every other spin. And then you see that as you add more and more sites, they will also contribute to the entanglement between the left part and the right part. Good. Good. Yes? Not identity. They're going to be like the ground state. So let us identical to the ground state. Yes. No, like look at this example here, right? So if you take these two states, they are orthogonal, but that we had this argument also before. I think David made this. So for many body states to be orthogonal, it's enough if just one qubit is different.
If you cut it through between the bonds, there's only one.
That's correct. If I just basically do another cut between here, then there would be a product state for this bipartition. Yes. Right. So one important takeaway message from this is that the entanglement is really basis and cut dependent. So, yes. Well, yeah, basis dependent in the sense that if I mean, the reason why I'm bringing this up is because of if I'm having a, it's right, it's cut dependent. The cut is sort of related to the basis. If I take, for example, real space, then I just do a real space cut. If I just go to momentum space, then that's why. But strictly speaking, you're right. It depends on the cut, but the cut itself is sort of very natural in one basis. Another one is yeah.
There's also there's a state, and I guess that's a statement of diagonalization. There's a state, let's say you wrote for the two dimers. There's a dark black on the left and the open on the right.
Yes.
Like you have two blocks and two opens.
Yes.
That's all there is.
Right. I mean, this is like what I.
Right.
I mean, I'm defining my dimer state in like as a belt state in this form.
Right.
If you have a singlet, if you want to have a singlet, then you would like up state here, down state here, and this would be for a singlet state.
Right. Okay, I see. Sorry, it's not a representation for arbitrary state, it's a representation.
For this one in particular. Yes? Yes? Right, okay, so the point is that every spin does talk to another spin, but there's still a decay of how strongly they're talking to each other. Because you're right, if you would think of this random state that I gave before, then there's no sense of locality, and every state, every degree of freedom is in the same way entangled with anything else. And in that case, you find the volume law, but here there's still a sense of locality, but you just have a diverging correlation length.
That's correlation length is inside the constant.
The
right? Like the bigger the correlation length, the bigger that constant.
which
Block C. That.
yeah, right. Yes, Shalusha? That's right, but the other way works. If you just have a short range correlations, you can say that you have. Wait. Now I'm confused myself. No, but for ground states, we can make the statement if we have in the ground state we have short range correlations. That's right, yeah. But these statements, right? So that's important. I mean, I wrote this also. So here I'm talking about ground states of local Hamiltonians. So then this is true if we just going, and we're going to see this also in a moment. Once you deviate from ground state, this is another story. But let me stick to this, and one could talk a lot more about this, but I want to get actually to introduce some algorithms, and that's why I just want to use this now as a motivation why ground states can be represented. And now, just to cut this line of argument short, so ground states have an area law, and now I want to make a statement that there's something special about area law states, because now if we have 1D area law states, if you have 1D area law states, then we can argue and also prove, in fact, that the Schmidt values decay quickly. quickly, and thus we can truncate the sum. Say again? Right, exactly. So basically what I can say that my state is well approximated by a sum of alpha going from 1 to some chi, which will be much smaller than 2 to the L half times lambda alpha times alpha A times or phi alpha B. Right. So this is the line of arguments. Ground states of local Hamiltonians fulfill an area law that can be proven rigorously. And moreover, it's not hard to show that if you have an area law, then the Schmidt values have to decay sufficiently quickly. And there's one small caveat. It's actually not sufficient to have an area law for the von Neumann entropy. It actually has to be for a Renyi entropy with an index actually smaller than 1. So there are some mathematical details, but overall, this is the important statement. Area law means Schmidt values decay quickly, and then we can now throw away a lot of data and get a good representation of the state. Now, and I want to show this briefly on a slide. So then you can just do some fun game or to visualize how well this can be represented by not thinking about quantum states, but by thinking in terms of images. And the way that I want to think about is the following: if you have an image of, I don't know, some person, now you could say that, well, the image is a matrix. So you can think of the image corresponding to a matrix Aij, where each pixel value corresponds now to the value on like the entry of on this matrix, right? So maybe a 0 is a black pixel and a 1 is a white pixel. And now if I just rewrite the Schmidt decomposition a little bit, so now I can say that, well, I have my amplitude in a many-body wave function, which is I1 through IL half, and then I have here IL half plus 1 up to IL, right? So this is now I'm grouping these indices together. So now I have I can represent my wave function by a 2 to the L half times 2 to the L half dimensional matrix. And this matrix I can now decompose in the following way. So now I can write this as a sum over alpha from 1 up to 2 to the L half. And then we have U I1 through IL half alpha times lambda alpha times V alpha IL half plus 1 up to IL, right? So this is now the Schmidt decomposition, or if right in terms of the matrices, it's known as the singular value decomposition. But now what we can do is we can say that, well, let us now truncate this one here up to some arbitrary chosen value chi, and just discard those contributions corresponding to small Schmidt values, and then reconstruct the image. And then we can just by our bare eye see how well this works. And this is what I prepared some demonstration. Is it readable somehow? Otherwise I can try to see, or can make it bigger. So here is like some Colab notebook. And if you just clicked on this link that I've shown before, you can be directed directly to these Google Colab notebooks and play around with it yourself. So this is now loading some, there's a library, and now we can here load an image. And here I'm showing the Frauenkirche in Munich in a pretty high resolution image taken from Wikipedia. And now I can just play exactly this game. So I define chi. Chi is now the number of states that I'm keeping. And now I'm doing a singular value decomposition. And then I'm reconstructing the image by taking only into account a certain number of Schmidt values. And we can first look at the image, left the original, right, keeping 2 out of 800 Schmidt values, and it's not easy to tell that this is in Munich. But now, and then we can also look at the distribution of Schmidt values. So here I did exactly what I argued before. So I just sort them according to their size, and we see that there's a bunch of ones that contribute fairly strongly, and then it just decays. So from this, we are somewhat hopeful if we just increase this number to something which is still much smaller than 800, maybe 50, and play this game again. So now we see that by taking 50 out of the order of 800 of the states, we just get at least a recognizable state of this Frauenchurch. This is now chi equals to 50. So now we just take 50 out of 800 singular values. But now this also depends quite a bit on what kind of image we choose. And this is now also giving you some intuition for what quantum states are good if you don't use the Frauenkirche, but you use some artist picture. So this is by, I think, Mondrian, at least an interpretation of this done by me. And now we can just do the Schmidt decomposition. And let's keep chi 50 for now. But now we see that, well, the Schmidt spectrum looks very different. Now we see that there's only order 1 Schmidt value, and all the others are 0. So we get a perfect reconstruction, but if we just use 1, it's still going to look perfect. So we see that this is like a way to see how much information is contained in art, maybe. So here we see that in this case, just a single Schmidt state is sufficient to represent the state complete. So this is the analog or the artist's interpretation of a product state. So good. The cut is between this basically here, like the x-axis would be the A part, and the right part, the B is the y-axis. No. I mean, so in fact, the maximally entangled image would be a diagonal. So, yeah.
Yes. Square matrix, then during the transpose of each other?
No. They are not related. I mean, they can even make, because this image that I was showing is not a square image. So it's actually the dimension is different. So here. In this case, I'm right. So what I'm showing here is for a square image. No, it even doesn't have to be. So just make like every matrix, for every matrix you can do a singular value decomposition, but not every matrix can be diagonalized. So that's more general. So in a special case that you have a diagonalized matrix, then you can write it in this form, but generically this is not. Even if it's square, it's not true for every. If you take a matrix which like if you take a nilpotent matrix, you can't diagonalize it, but you can still do it. Good. So that was just there to motivate basically this the story a bit, and the important takeaway message is like area law for ground states of local Hamiltonians, and area law states automatically means that the Schmidt values decay very quickly. So ground states are a bit like these Mondrian pictures. So we are very hopeful of doing this compression. And in other words, it means that ground states of local Hamiltonians are in a way very close to being a product state. Right? So instead of just taking only one Schmidt value to represent it, you need a handful, but not infinitely many or not exponentially many as you would need for a generic state. And now I want to, based on this knowledge, now argue that it's useful to have matrix product states. So first, just to see the similarity, if you have a general product state, so now you might say that, well, you have some Hamiltonian and you want to use the space of product states as variational space, then all you have to do is you just can say that, well, you express the amplitudes in your many-body wave function as a product where you have product phi1 I1 times phi2 I2 up to phi L IL, right? So this would be just an ansatz for your wave in terms of a product state. And now if you have this ansatz, the number of parameters is now just proportional to L times D, right? So you just significantly brought down the number of parameters, which in the full model was, if you recall, is like D to the power of L. Now, matrix product states are almost the same thing, except that we're just replacing these complex numbers by matrices. So now, if you have a matrix product state, what we're going to do is we say our phi is equal to phi I1 through IL is equal to just the product of matrices. So we have matrix I1. Now this is a matrix product A2 product blah 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 to A L I L. And now, well, if I just multiply these matrices, right? So these are chi times chi matrices. And we see that if you just multiply these matrices together, that would not be a scalar. So but we just multiply now a vector here on the left and a vector here on the right. So that this gives us a complex number, right? So now we see that, well, we choose here something for our indices, like maybe some, like for a spin, like for a qubit system, this would be just a bit string. And then we say that psi of some bit string is equal to some complex number. And this is a complex number which I get just by multiplying these matrices to each other. And then I have something to terminate it. And now, clearly, the space of states that I can represent is much larger than this one. So every product state is, of course, included in this one where I just have one by one matrices here. So now let me just give you an example. Like an example is the GHZ state. And the GHZ state would be 1 divided by square root of 2 times up, like all spins up, plus 1, 2, 3, 4, 5, all spins down. So this is a state which is clearly not a product state. It is an entangled state. So we can't represent it in terms of a simple product state. But this is a state that we can easily and exactly represent in terms of a matrix product state. In particular, if I choose now my matrices A, let me see, A up, I just choose to be 1, 0, 0, 0, and A down, I choose to be 0, 0, 0, 1, and my vector VL, I choose to be just a 1, 1 transpose, and my V right, I choose to be 1 divided by square root of 2, 1 divided by square root of 2. So now you see that if you choose these matrices with these kind of vectors, that we exactly get this matrix, because you can easily check it. Because now if you want to evaluate, so say what is the amplitude psi of all spins up, then we see that, well, this would be A up, A up, A up, A up. And then you see that, well, if you just multiply these together, you just multiply these ones, and then you just get exactly 1 over square root of 2. But if you just flip a single spin, then you would have these matrices, but suddenly one of those shows up, and then the whole thing collapses to 0. And the other way to get it, the only other way to get it to 1 over square root of 2 is if all of the matrices are this down matrix. So this is just one simple example where we can see that there is a state where we can represent it exactly in terms of an MPS. And there are many other states where we can find an exact representation in terms of an MPS. Another famous one, which is the AKLT state, or the Affleck, Kennedy, Lieb, and Tasaki state, where you can convince yourself that this is a matrix product state, and there are some details in the lecture notes. But besides this, you can just come up with various interesting Hamiltonians where you just know exactly how to write down the great ground state as an MPS. Now, what we are doing now is that we want to now consider general Hamiltonians where the ground state can actually no longer be exactly written as an MPS, but well approximated. And going back to this argument that I made before, by basically saying that, well, and I now just assume that the states, and basically from this analysis of the Schmidt decomposition, I found my state is fairly close to a product state, and that's why I just assume that this is now a good ansatz for area law states. And the key idea that I want to follow now, key idea is that assume that the states we are interested in can be well approximated. By MPS. And this is the case for all area law states. And I, again, leave this maybe now as an exercise, but you can show quite easily that if you start now from a generic many-body wave function, or the amplitudes in a generic many-body wave function, what you can do is you can now successively do the Schmidt decomposition starting from the left to the right, and always just represent the state in terms of the basis of the Schmidt states. And by this, you can then sequentially turn the amplitude of a many-body wave function into a product of matrices. And if you look in the links, there's also a Python script which is actually doing this. You can just feed in whatever wave function you have, and just by sequentially doing the Schmidt decomposition, it's actually constructing the MPS approximation of the state. But this is not the route that we want to follow, because that requires you to have some other means to actually get the state so that you can compress it. And now I want to discuss some algorithms which directly work in this manifold of matrix product states, and then allow you to do operations with these states. Good. Yeah, because I want to show. Yeah. Thanks. So for these algorithms, we're excessively going to use the tensor notation, but this is something that you already seen in previous talks. Tensor notation. Namely, before we thought in the context of unitary, like these unitary or these brickwork circuits, but in general, we are saying that, well, now if we have a scalar, like a scalar, like A corresponds to just a blob. If you have a vector, it corresponds now, like from vector Vj, corresponds now to some blob with one leg sticking out, and a matrix would be now like a matrix Aij would correspond to a blob with two legs sticking out. And if I if I'm doing some tensor operations, so let's say that I want to just do a matrix multiplication. So then I would say that, well, B I J is equal to the sum of A I K, so C K J, sum over K. Then this would correspond to just having the two blobs. So this one here would be A, this one would be C, and I'm just merging the corresponding legs. Right? So this is exactly the same what was used in these random circuits. So, but now I can use the same language to represent my matrix product state, right? So recall for the matrix product state, I have my amplitude psi I1 through IL, and that's given now, if I just actually write it out, so then I have now the product of all these matrices. So I have here now the sum over alpha, beta, and so on. And then I have here my matrix A with some index I1, and then I have here my index alpha, and then I have here the next matrix A, alpha, beta, I2, and so on, right? So now I have this product of these many matrices, and here I have my order L tensor, but now I can actually just use this tensor representation or this diagrammatic representation to represent my matrix product state. So the wave function, the many-body wave function, is now a blob where we have L legs sticking out. And now I'm just writing this in terms of a matrix product state, which is now 4. So we just multiply the matrices and we just leave the physical leg here untouched, right? So now we have a representation of our many-body wave function. It's an order L tensor represented as a product of these order 3 tensors. And then you can also make a sanity check. If you just see after contracting all of these tensors, you're actually getting back a tensor which has the right number of legs. Otherwise, there's a problem.
So that last thing is that's your B left and B right.
Exactly. So I just write. So right. Thanks. So here I just assume that this already has this contracted in. So, but in what I would have to do exactly to just to be very consistent with the notation I used before, I have my V left vector here and my V right vector here. Yes. Thanks. But if you just look at the literature, I usually just leave this one out and you say that, well, this one is already contracted in.
It only has one index.
Yes. Good. So now, and just to warm you up for what's about to come, because now we can do lots of calculations with this kind of formalism. So one simple one would be to just calculate maybe the overlap. So if I want to calculate the overlap between two wave functions, between a wave function psi and a wave function phi, now using this in terms of the tensor notation, what that means is I have like one blob representing the wave function psi, and I have another block representing my wave function phi, using like this notation, and then I just have to sum over all of those legs. So this would be now the overlap of those wave functions. But now I can also do this using my tensor networks. And for the tensor network notation, it would like 1, 2, 3, 4, 1, 2, 3, 4, 5. So let's add one more here. So now the tensor network notation, this is how it looks like. And similarly, if I want to calculate some expectation value of some, say, local operator O, I just have to squeeze it in somewhere here. So this is now my operator O acting here on a single qubit. And then this would be just something like this. And now there's one important observation, that this can actually be done efficiently. And what I mean by this is now the following. If you are in the language of this dense wave function, of the full wave function, calculating this, you actually have to sum over all of those legs together, and you would find that just the number of operations needed for doing this multiplication is exponential in L, because you need that many loops to do this calculation. And now the question is, like, if you want to calculate it here in terms of this MPS representation, one trick is that you can now do this, say that you start at the left and you now one by one multiplying these tensors, then you can see that if the state is given in this matrix product state formulation, that you can now calculate expectation values efficiently. Here I'm just making this more as a statement, and the proof is exactly just by seeing how we construct it. But this is an important statement because we know that we can represent a wave function efficiently using this kind of formulation, but we can also calculate observables efficiently. And this is, once you go to 2D, you see it's no longer the case. In 2D, if you have some generalization of matrix product states to 2D, you still might be able to represent the state very efficiently, but yet calculating observables is also exponential hard. So here for MPS, we find that we can represent the states efficiently. And also, once we have a state in this form, we can calculate observables efficiently. Yes?
What does it mean? I mean, the wave function is defined by its matrix product state.
Yes.
So what does it mean that, let's say the first statement, like, what does it mean that, where there's an exponentially hard calculation to calculate that efficient?
Right, so let's do the following. So let's say I have my matrix product state, and if I want to now calculate my observable, and let's say that I would first multiply all these matrices together to get my wave function psi, and then I multiply the other guys to get my wave function phi. And now you see that like on the way of constructing the full wave function, you would actually have something that is exponential hard. So you have to be smart by doing these contractions in the right order. So that's a subtle part, but this is maybe quite important that you just can do it in this way to efficiently calculate observables. Yeah, and if you just go to 2D tensor networks, you see that this is no longer possible. In fact, you can prove that this is exponential hard. So even if you have a very powerful friend who just gives you the solution of the 2D Hubbard model and gives you the tensor networks, you would still not be able to calculate any observable exactly. Yes?
The problem of like finding the tensor of the efficient.
Exactly. This is what I'm going to talk about next, because this is exactly thanks for this question, because now this is exactly the point. So now what I've shown, ground states have an area law. Area law states can be efficiently represented. And if I have a representation of the state, I can actually calculate observables. So this is as far as we got now. But now the question is like, how, given some Hamiltonian, how can you do the time evolution, or how can you actually find the ground state of some Hamiltonian? This is exactly where I want to get to. Yes?
Let's say you don't have the Hamiltonian, but you have kind of the reverse of this problem. Like basically the tomograph. Like I give you the expectation value of like n like polynomial number of this states, and you know the state is a tensor network. Can you now give me the like solve those equations for efficiently as well?
Right, that would also work. You can basically, I mean, this is like something similar is done in this. There are works by Miles Staudenmeier, for example, where they use MPS as classifier. Then you have just basically some input, and then you can, based on this input, you then train and then find the state that's optimally giving this kind of distribution back.
So
yes?
In your 2D model, you can always like imagine MPS as a snake that traverses all the.
Sure, but then you're just effectively representing it in terms of a 1D problem.
I guess so. What makes it so hard to calculate 2D observables? Because
well, you can just draw it like just basically here. I found a way to do this, to calculate this expectation value without having to construct a high order tensor in the meantime. That's basically showing that this is efficient. Now, if you have a 2D tensor network, like tensors, and now I want to calculate basically the tensor trace, right? So now I want to contract all the tensors, but now you see there's no way to contract it in such a way to not have many, like a very high rank. Let's say that here I'm just terminating with something, and I know if I done the whole thing, it's just a complex number, right? So if I just contract everything, this is just a number, that's good. But there's necessarily in the meantime I have something which has like some exponential number of, has basically in the area, yes. There's some exponential. It's not as bad as exponential in the volume, but it's exponential in the area, and that's already bad for us. So yeah.
But it's actually, in that sense, not different from that. It's also
Well, but what MPS do is basically MPS reduce your 1D problem to a 0-dimensional problem. And that's, we know how to solve. But in 2D, you can basically reduce a 2D problem to a 1D problem, which is then still hard. And then, well, the way to actually go over it is to then reduce this 1D problem again to a 0-dimensional, but then you need to do some additional approximation, which sometimes is hard because you don't necessarily have the area law story for this. Because not every tensor networks give you gives an area law on the boundary. Good. So now, before I'm introducing the algorithm, I need to do some more technicality. And this is the following. What we are interested in are the amplitudes in the many-body wave function. So this is now what makes our physical wave function. So these are the amplitude in the many-body wave function. But now we see that there's a gauge degree of freedom. Because if I say that, well, I'm now not writing the indices. And let's say that we have now some matrix AI describing my quantum states by multiplying all these matrices together. But now what I can do is I could say that, well, let me change it by taking some invertible matrix X and now change it to this. Right? So now we see that if we just multiply those matrices together, we will get exactly the same amplitude, but yet the matrices are different. So we have a gauge degree of freedom that allows us to choose the matrices in some way that's convenient to us. And now I want to pick a gauge, and this is known by the name of kind of canonical form. And the canonical form is now doing the following. I'm choosing my matrices in such a way that I write each matrix AI in terms of a matrix gamma I times lambda. And the gamma I is now a matrix relating the local and Schmidt basis. And my matrix lambda is just a diagonal matrix containing the Schmidt values. Diagonal matrix containing my Schmidt values lambda alpha. So it's not hard to see that every MPS can be brought in this form by just simply doing successive Schmidt decomposition coming from left to right. But this is now a form that we find very convenient, and it's very convenient for the following reason. Because now we remember from the discussion that before that the Schmidt states are orthogonal. And now if we have our MPS given in this canonical form, right? So now our MPS looks like this. So we have our tensors gamma, and on the diagonal we have our Schmidt values lambda. So now we see that if I break this apart, so I'm just saying that, well, I break this apart. So now if my index alpha here and index beta here, then I have here my matrix lambda in between. But now I see that by multiplying all the tensors left of my cut, I'm exactly getting back my Schmidt states phi alpha A. And if I'm multiplying everything on the right, I'm getting my Schmidt states alpha beta in this case. And I have here my Schmidt values lambda alpha times delta function lambda. Right. So the thing is that if we have this canonical form, which I can always choose using this gauge degree of freedom, I can now directly relate my indices of these matrices to the Schmidt states. And this has now some really cool consequences, because now I know that my Schmidt states are orthogonal. So I know that phi alpha prime is a delta function alpha prime. And now if I just write this in terms of my MPS, this would correspond to something like this, right? So if I just have here my gamma lambda gamma lambda gamma alpha prime. So I find that these states here are always orthogonal, and I can now use this identity successively, for example, for calculating expectation values. Right? So previously I was saying that, well, if I have an expectation value of something, right? So then I have here my gamma lambda gamma. I drew too many. So now you see the point. So this now continues, and now you see that whenever I have these guys, this will give me an identity, so I can just remove it. So basically the identity is this form, that if gamma lambda, that this is an identity. And this is directly inherited from the fact that the Schmidt states are orthogonal. So we see that I can now remove this one, turn this to an identity, and then I can use this identity again and again. So what I eventually see is that calculating expectation values is now very simple. So if I have now my expectation value that I want to calculate, I can just calculate it in this form. I've got lambda squared gamma star. So the key point that I wanted to point out is that if we choose this particular gauge, where we just write our tensor, we will write our matrix product state in terms of gamma matrices relating the Schmidt basis and the local basis and the Schmidt values, then we can now calculate expectation values very easily by using these identities. Yes? No, that works in general. Here I left out the indices because it's too many indices, but you can also show the same thing, right? So because the Schmidt states are orthogonal no matter what, right? So this is the only thing that's important here. So that identity works for even for systems which are not translation invariants. Yeah. Yes. So you just can, every state can be written in this form. Yeah, exactly. Yeah, of course, if you have a state where if it's with translation in the way that it doesn't have only partial and area law, then it won't. So if you, but once you are happy, like once you write your state in this form, like once your state can be written in this MPS form, you can always, without loss of generality, bring it into this form. Well, they are not right. So you can always bring it to this form and that it works. If, however, you are destroying, now you have this state, now you truncate maybe on this bond, then you have to just bring it back to this form. Right, but here I'm not doing any truncation. So here I'm saying that I'm taking MPS, I can bring it exactly into this form, and then I have this, all the benefits that come with this form.
System is non-uniform and entanglement, we can have different bond dimensions.
That's perfectly fine, yes. Right. Exactly. So an extreme case is the one, or this dimerized state, right? So then we would have a bond dimension D and 1, and D and 1, and D and 1. Yeah. Good. So Now I'm a little bit in trouble because I'm not going to get as far as I wanted to. So, but that's hopefully okay. So let me just at least give you a rough idea of what's about to come next. So, and then now what I want to do is I want to introduce this the time evolving block decimation algorithm. Time evolving block decimation. The first part I can probably shortcut a little bit because you've all seen brickwork circuits quite a bit. So now what I want to do is I want to assume that my Hamiltonian of interest is of the following form. So it's of the form that I can write as h I plus 1. Right. So we have now a Hamiltonian that only acts between nearest neighbors. So we have like so my Hamiltonian then acts maybe on these sides like I and I plus 1. And if I have a Hamiltonian of this form, I'm now interested in expressing my time evolution operator, right? So now what I want to calculate. So now we are interested in applying e to the minus I t h, or alternatively e to the minus tau h for imaginary time evolution to some state. But now, and this has been mentioned before, what we can do is we can now take our time evolution operator and perform a trotter decomposition. Right? So now we can trotterize this, and now again using exactly the same notation as was used before, I can now approximate my time evolution in terms of a trotterized Hamiltonian, where I'm just alternatingly applying my right. So this is now one time step for some delta t, and now I can approximate my time evolution in terms of these brickwork circuits. Right? So this is a part of the motivation for also choosing these random unitaries, where you just have something that looks like a evolution with a local Hamiltonian, but except you're just replacing it by random unitaries, which makes it, as you learned, exactly solvable. But now we don't have this case. Now we have a specific Hamiltonian, and each of these gates here corresponds to simply e to the minus I delta t times my h I plus 1. Now, if I have this kind of evolution, I might ask now the following. So now I'm already quite happy with my graphical notation of tensor networks. So now what I have is I have now my MPS, and this is now my MPS at time 0. And now I want to time evolve it by just doing one time step, like one time step delta tau. And what this amounts to is that I just take my circuit, and now I'm just applying one set of trotter gates to it. Right? So this is now evolving it by some time delta t. And the big question is now how, like, because I'm starting from an MPS and now I apply something to it, and that will increase the entanglement on a given bond. What I want to do is I want to bring it back to this form, right? So I want to take my MPS, which maybe has a bond dimension chi here, and I want to just bring back this thing to a MPS with a new bond dimension. Let's call it chi tilde. And I want to do this in an optimal way. If I just keep, and I think David mentioned this, if I just keep contracting this exactly, then I will actually find that the bond dimension that we will get would grow exponentially on this if I just keep going. But I want at each step find back the like an optimal representation of the state. And the key idea of the time evolving block decimation is now the following, we are just first, we are doing this now sequentially. We say that, well, we start with our state, and let us now first apply a gate on the first bond and do this in an optimal way so that we just absorb this into the state. And then we can go to the next one. And then we just do it sequentially. So what we can then boil it down to is that we have a problem where we have our MPS, and we just apply to this MPS one gate, which is doing the evolution, and we just have to bring it back to an MPS. And this is now the problem that we have to solve. Right? Briefly repeating, so we want to do the time evolution. The time evolution, we know we can express in terms of this brickwork circuit. And the brickwork circuit, we can now just sequentially apply. We just first apply the first gate, do a compression, we do in the next one, we do the compression. But what we have boiled it down to that we just need to know, figure out how can we apply a gate to a given bond. And this is the core of the TEBD algorithm. And here we can now make use of this canonical form to do it in a very simple way. And now, using the canonical form that I had before, I was pointing out that these gammas and lambdas are chosen in such a way that if we just cut a bond, that this corresponds exactly to a Schmidt decomposition. And if I just now contract all the stuff here on the left, I'm getting the Schmidt states. If I'm contracting here everything on the right, I'm getting the Schmidt state for this given bond, which are forming an orthogonal basis for this subspace, for this part. So now what I can do is I want to say that I want to apply now an operator to two adjacent sites, right? So now I have my two adjacent sites. I have my gamma, lambda, and now I stop here, right? So now here I have my index alpha, and this index alpha refers now to my Schmidt states phi alpha on the left. I have here an index beta, which refers to Schmidt states describing stuff on the right. And I have here some state referring to states I and j. Right? So here I have the local states, and here I have the Schmidt states. So what I'm effectively doing when I'm just writing if I just kind of contracting the tensors here to something which I now call theta. Right? After contracting this, I'm calling this now this blob theta. And this is now a representation of my full wave function in terms of a mixed basis. So I just having here alpha, beta, I, and j of theta, I, j, alpha, beta times, and then we have states phi alpha left, I, j, phi beta on the right. So graphically, what it means if I take my one-dimensional system, if I take my one-dimensional chain, I'm describing everything left of my sites that I'm interested in terms of Schmidt states phi alpha. I'm describing everything right of my spins that I'm interested, or sites that I'm interested in terms of my Schmidt states beta for a cut at here and this bond. And the local sites are expressed in terms of a local basis. Right? So using the properties of this canonical form, just by pulling out some of these matrices from my matrix product states, I get immediately a representation of the full wave function in terms of a mixed basis. And now, and I guess I'm going to discuss this in the lecture next. the lecture tomorrow, that what I can do is I could say that, well, now I have my wave function this form, and I can immediately apply my unitary evolution. So I can now evolve my wave function after I brought it to this representation in terms of this mixed basis. And at this stage, I can now project it back. And all I have to do is to perform a Schmidt decomposition of this object. And after doing the Schmidt decomposition, I can do the same as what we did with these images. I can then say that, well, I just do a Schmidt decomposition, or I'm doing a singular value decomposition. And then I can now say that, well, I'm now only keeping the dominant singular values, and all the rest I'm throwing away. And by this, I can then reduce the bond dimension, and I can actually, at each step, tell how much I've thrown away. And then I can control how well the approximation works. And let me just very quickly, just in case you have some time tonight or some interest, you can have a look at one of these tutorial files already, because now there's another file, which is this TEBD. And this TEBD code, which contains all the core functions already, which you need for doing these simulations. And there are many of them you can already understand with what we discussed. So there's one function which is just initiating a simple product state, right? So this is just now initiating a product state of a simple ferromagnetic state. So this is a function which is returning the MPS of a simple Ising ferromagnet. And then it has a function which is just initiating the Ising Hamiltonian. So it just constructs the two-side Ising Hamiltonian and constructs the bond evolution operator, which is just e to the minus delta times h. Right? So then you just have already the ingredients that you need for evolving one bond. And then it has now functions for calculating these expectation values. So here, for example, for a side expectation value, this is exactly the type of diagram that I've plotted here. So it's just using properties of this canonical form and calculates the local expectation value of the SZ operator, for example. And then there's a function which is just returning the entanglement entropy, which is just simply using the Schmidt values and calculating from the Schmidt values the entanglement entropy. And then it has one function which you don't understand yet, but this is what I just basically at least gave the idea. So there's a function which is now applying one unitary operator, like one unitary gate, to the wave function in this mixed representation, which we just get by contracting these handful of tensors, and then performing a singular value decomposition to project it back. And that's literally all we need for doing MPS simulations, because then with this, we can, for example, do some experiments. So we can now, for example, do a real-time evolution where we are just calling this TEBD function and using it for evolving a simple product state. And then we can see how the entanglement entropy evolves and how the bond dimension required evolves. Or we can do imaginary time evolution for example, finding the ground state of the Ising Hamiltonian. But I'm going to discuss this in more detail tomorrow. But if you want, you can already have a look at the code today. Yeah, I think I should stop now. Yeah. Thanks.
We'll probably say this next time, but the truncation, of course, messes up the normalization. What do you normally do? Just truncate it and then multiply it by a factor to bring it back up, or do you do something more sophisticated?
Right. So yeah, that's a good point. So indeed, this kind of which I already mentioned is that if you're having this kind of nice canonical form and you are just truncating somewhere here, then it's no longer in this canonical form. The thing is that when you are doing these time values, you're usually doing it by fairly small time steps to have a small trotter error, which means that the error that you get from kicking it out of this canonical form is really small. So it's not the optimal truncation that you're doing thereafter. but it's pretty close to the optimal one. And empirically, you can, of course, after each step that you evolve it, you can bring it back to this canonical form, which takes a certain computational effort, which is not large, but you can do it. And then you see that the gain that you have from bringing it exactly back to the canonical form is fairly small.
So you don't bother doing that?
No.
Let the state become not properly normalized and everything's fine?
Yeah, but the thing is that you do it iteratively. So you just basically each bond, right? So basically, let's say that you are sweeping through your system and you're just doing some operation here. If you're doing some truncation later on here, which kicks this one out of the canonical form, but by some small epsilon. But then soon you're going to be back at this bond and you just bring it back to this canonical form. So this is how it works, right? So it's not that you are just letting it go. So you will always at some point return to this bond to just push it back to this canonical form.
Putting it in the canonical form is also fixing the normalization.
Yes, that's right. No, that's the important step. So whenever we are doing whenever we truncating it, we at the same time would renormalize it. Right. So if
and that's just a multiplication.
Exactly. So we just say that we just exactly. So we just yes. Uh-huh.
Every count.
Yes, exactly. So let me see if I. No. Let's say that you have an MPS which is not in this canonical form. Now we would just start at the first bond to do a singular value decomposition, and the singular value decomposition of this guy just scales as the third power of the matrix dimension. So that's, I mean, in this TEBD algorithm that I've put up there, the SVD is the most expensive part, but it's not really part, right? So it just takes a few seconds for a thousand, for a few thousand times few thousand matrix.
So you do it for every cut?
Then you have to do it for every cut. So you just do it for this cut. You just bring it into then you get here gamma lambda, and then you have to just do it sequentially over and over again. Right. So if you don't have any additional structure for the MPS on a laptop, you can. If you have a laptop and you want to take a few hours for doing the time evolution, you can just use bond dimensions of a few thousands. Oh no, but the number of sides doesn't really matter. So it's, if you just do this, it's just linear in the number of spins. So that doesn't cost much time, but it will be cubic in the dimension of, right? So it's linear in time, and it's cubic in the bond dimension. So this is what getting more expensive, and here, I mean, you can just use and also linear in the time. Yes. But again, I mean, in these tutorials, these are exactly things that you can also play around with on your laptop or on Google's machine. Yeah.
But Chi is growing in time.
Chi, right, and this is also what we're going to explore, and that will depend a lot on what kind of problem you are looking at. Right? If you, for example, take a many-body localized Hamiltonian, you would see that this Chi is growing very slowly. If you are looking at a highly ergodic system, in the worst case, you're just looking at at random unitary evolution, the Chi would grow really quickly. So that will then become very much model and problem and initial state dependent. It's exponential in time. In the worst case, it's exponential in time, and but for MBL system, it might be some power law. So well, for MBL, it doesn't actually saturate. It's still it goes algebraically. For exactly. Right. So So overall, you can say that the chi or the bond dimension needed is exponential in the entanglement entropy as a rule of thumb. So then, depending on how your entanglement grows, you will have a bond dimension which has to grow accordingly. Yes.
For the image, the image with the diagonal like black into the diagonal, that's kind of.
That would be the maximally entangled image. Yes.
You see that there's not that information. Like if I rotate the axis, then just.
That's right. Yes.
Then, like, is there some analogous in like tensor networks that maybe there's like, and I think there is a measure.
No,
they give you the matrix and like it tells you that this like image doesn't have that much information. This one does, and that probably doesn't depend on its rotation.
Right. I mean, yes, this is true. Like so if you take a free fermion state, right, or then, or like take a Slater determinant. The Slater determinant, it would be a product state in momentum space. So in that case, you would say that, well, going to momentum space, it's just a really, really simple state, but it might require an infinite bond or like a really, really large bond dimension if you just do a cut in real space. So yes, it really depends on what kind of, and that right. So basically, if you take an image which is like a diagonal line, you rotate it to a horizontal or vertical line, that would, in this case, maybe correspond to a rotation from a momentum space to.
But I guess like there is a classical algorithm for images that I just give the image to the algorithm and it tells you whether it has really a simple like description or not, like whether there is some rotation or something. Like I think there should be an algorithm that tells me this image, how much information this image has, like which would be the high number for like the actual picture of Munich, but like something simple for here. But like I wanted to see if there's some similar algorithm for things like this tensor network or quantum space, because like
no, this is a good point.
I didn't know that if I go to the like momentum space, I would get a simple representation. That there is an algorithm that tells me there exists a simple representation of the state if I didn't know that.
This is a good question. I don't.
Yeah,
that would be already had no, but
do these methods in momentum space, and that's actually really very efficient, or is
well, there's a problem, right? So actually, this has been
non-local in momentum space.
Exactly. This is exactly the problem. This is exactly the problem because
it doesn't help, really, right? Even if
exactly
it makes the state simpler, but the dynamics and the Hamiltonian are very complex.
Exactly. So if you just maybe because naively, if you just don't think very deeply, you might say that, well, if you take weakly interacting models, momentum space representation might be really good for DMRG. Exactly. So but then what you see is that you look at the entanglement of the state. What you will find is you will get some volume law with a small coefficient corresponding to the small interaction that you have. But since it's a volume law, and if you just make the system larger, that immediately becomes really bad.
And it would just be logarithmic.
No, wait. If you have
it's a Fermi, I'm talking about the ground state of say a 1D.
Oh yeah, right. If you just if you just but now I'm just talking just the 1D, right? So now we are just talking in 1D and 2D, yeah, probably 2D.
In 1D, so you would have a logarithm.
That's right, yeah.
If I did it in momentum space, it would actually be volume.
That's right, yeah.
So you don't, even though it's
exactly, even it's like really interacting. Exactly. So if you're on at the moment that you go to. Well, I mean, one thing that we know, and in one case where it does help, is the following. This was also mentioned, like if you want to represent 2D systems, we like to just put it on a cylinder and make it effectively. And then one trick that actually gains something is that we say that, well, we're just using real space representation in this direction and using KY here, because then you have additional conservation laws that you can use. And then it actually helps because we anyway have an area law in this direction. There are 2D area law. Yeah.
Like corresponding momentum space in general cases, like optical phases. Quantum chemistry do a lot of optical.
And why does it work?
It works in many cases.
But why? I mean, but there's a, but then the Hamiltonian is very not, but, or is it that the Hamiltonian that you have are also not super local in real space?
Oh yeah, well, it's not as good as.
No, but I think that's basically right. So that might basically the. Mm-hmm.
Yeah.
Mm-hmm.
Well,
And it's just that if you just working with different functions and
so for EMRG and particle spaces is better than string functions.
Yeah.
Yeah.
Right, no, but I think this is the point, because in our case, it's super local in real space, usually, if you take a Heisenberg model or take a Hubbard model, but then it becomes very non-local in momentum space. And maybe for quantum chemistry, it's not such a contrast. Yeah, yeah, exactly. So, yeah.
Area law entanglement implies that there is an approximation of an APS.
Yes.
And you said that you qualified it by saying that it actually works for any entities for n less than 1.
Yes.
Is there an example where a state has?
Let me just quickly, right? So let me just quickly. The statement is that I was talking about the von Neumann entropy, but more generally, it could have Renyi entropies like S alpha, which is 1 divided by 1 minus alpha times the logarithm of the trace of rho to the power of alpha. And if you just let alpha, like basically for alpha goes to 1, then you just recover the S von Neumann entropy. And the statement that I made is that if you have an area law for Renyi entropies with an alpha, which is smaller than 1, you just can make these rigorous statements about the states being efficiently representable in terms of MPS, but not for alpha actually being 1. And I can't come up with a very good example. I mean, one fun fact I know where you see that there is a big difference depending on this value of alpha is for the following case. If you take a random state where you just only take random amplitude but not random phases, right? So you just take a random vector of only positive random numbers, then that state will have actually only it will have a volume law for alpha smaller or equal 1, but for any alpha larger than 1, you actually will find that it's a logarithmic entanglement. So this is one case where at least you get close to having but they see it's a it's a volume law, but with a coefficient smaller for alpha equals to 1.
Area law, but
no, the other way around. I mean, for alpha larger than 1. So there are some bounds, like the alphas with the smaller one bound to ones for larger ones. But I don't know any example where alpha equals to 1 gives an area law and alpha actually smaller than 1 gives a volume law. Maybe someone does. I don't. Yes.
For the 2D system, not even for area law, but O1 entropy and MPS.
In 2D?
Yeah.
Yeah, I mean, for 2D, a trick that is used a lot recently is you just basically take your 2D system and you wrap it on a cylinder. And by this, making it effectively a 1D system with long-range interaction, right? So if you take your system on a cylinder and you would say that, well, you have just nearest neighbor interactions, and you would say that, well, now you just map it to a 1D system by, for example, just enumerating the sites in this kind of snake form. But now you see that something that's really local in 2D becomes actually long range in 1D. So basically, at the cost of including long range interaction, which yield more entanglement, you can map a 2D system to a compactified 2D system to a 1D system. And that, in many problems, helps to get a better understanding, but that's not a genuine 2D method. Yes. Right, the strategy about how to truncate it's again, it will very much depend on what kind of problem you're looking at. I mean, I remember some problems, if you just want to get some scaling right of some, like the scaling of the entanglement entropy right, that might be super sensitive and you have to be super careful. If you're just interested in local observables, you just might truncate a bit more. But in practice, the way to do it is to just literally look at whatever observable you're interested in, and then make sure that it is converged in terms of the bond dimension. Just do your simulation and do it again and double the bond dimension and make sure it doesn't. I mean, this is, I think, what's done in practice. Because anyway, I talk about this also more tomorrow. Yeah, thanks.